So I just figured out how to invite you on the Autodesk Corsair website. So, but I encountered problems. There were 10 students cannot be invited at this moment, but there are 9 have been invited successfully. So is there anyone who received the email from Autodesk? No? Anyone? Okay. Have you checked your RIT email address, email box?
When would this email have been sent?
I think within 1 hour. I just did it. Apparently there are some issues. I mean, I will contact their technical support from Autodesk, see what's going on there. Hopefully it can be resolved in next couple of days. I think, I mean, it takes me a while to get this set up, but still there's a little problems. But I will make sure it will be resolved. Yeah. So let's start our lecture. Okay, so in last class, we talked about the very critical computation in the photopolymerization-based processes, which is the laser exposures in Ryzen, right? So we have this equation, sorry. And let's recall our memory about this equation. So we have some of the parameters here. PL, the laser power, and the W0, the Gaussian half width of the beam. Also the velocity of the beam Vs, and also penetration depth dP. So these are the parameters, and among the 4 parameters, PL as well as the Vs are the one we could control, right? And for the penetration depths, also the critical exposure, these are related to the material property of the resin. So usually it can be obtained from experiment. So as listed here, right? So we have a little computation using this equation. So a very simple one is, let's say you have depth, and you have a y coordinate. If you look at this figure, so basically this shows a cross section of the cured trace, and the upper half is how the laser beam look like, but also in the cross section view. So if you want to tell what is the laser exposure in the millijoule per square millimeter, what you want to do is input its depth and also the coordinates on in the y direction, together with the all these known laser power Gaussian half diameter, also the W0, the laser power. I mean yeah. This is the Gaussian Gaussian half diameter. Also the velocity of the laser scans, and the penetration depths. So you can easily substitute these knowns to this equation, And it turns out you will have the laser exposure at this specific point. So that's the simplest applications to use this equation. But there will be more to consider about. First thing first is this critical exposure. So that gives you some idea what will be the width of the cured trace at the surface. So basically, if you have a laser density less than this critical exposure, then there will be no curing take place. And that is, again, this EC can be figured out through some experiment. And when you check some resin material, it will tell you this. And another point is the scan pitch. As we mentioned in the last lecture, there are two scanning pitch. One is the layer pitch. Another one is this basically that is the scan pitch, right? So the layer pitch represents the overlap of the cured region among layers. And the scan pitch actually it describes this overlapping for the same layer, but among different scanned paths. So definitely you want to minimize these void, right? In between of each of the traces, and also to get in between of the different layers. So you definitely want to have a appropriate pitches. I mean, both in both layer, in both between layers and also between the traces. So this is critical to tune when you have such a process. Also, there could be some variations in computation, in calculation, when you have this laser exposure equation in the resins. So first of all, how you compute the maximum cure depth. So basically it measures this CD, right? So when this CD happens, you will have the maximum laser exposure. And also you have this EC, which is the critical exposure. And by substituting them together into this equation, you will have this maximum cure depth. Then you may ask how you get Emax, right? So the Emax actually is the energy, is the laser exposure at 0.00, which is this point. So in principle, if you have a laser scan and the maximum energy exposure will happen at this point. So by substituting the coordinate, which is the depth and the y coordinate, into this equation, you will easily get this Emax. And also, sometimes if you want to, if you have known a desired cure depth, you want to determine the laser velocity, because we discussed if a slower laser velocity usually will cure more resins, right? That's intuitive. Basically, you are exposed the resin into the laser more time if you have a slower laser velocity, right? So, but if we have a desired depth, cure depth known, and how you determine this laser velocity. So basically what you want to do is substitute this CD and to this equation, and it turns out you will have this laser velocity come up. So that could be another way to utilize this equation. So for example, if you already have a velocity determined, then what is the desired QL depth? Basically, this becomes known and this becomes unknown. So again, substitute the known to this equation, and it turns out you will have this unknown solved. But basically, that's the inverse way. If you know the desired depth and compute this laser velocity, right? That will be the opposite way, but similar process. Use the same equation. So any questions so far? Okay, good. So let's look at some of the example, further example. Where is it? Oh, that's I think we have a question about. Just 1 second. Let me find it. Yeah, it is. It is here. So, sorry, that could be another question. For example, still using this this equation. So let's say you have everything known. Laser power, Gaussian half width of the beam, velocity of the beam, penetration depths, and also this critical exposure. Then the question is, what is the width of the cured line at surfaces? Basically, it's computing, it's asking you to compute this width. This. So what you want to know, what you want to compute is, so that is okay. At this point, actually, it's exposure, laser exposure is exact EC, which is known, right? And what is the coordinate at this point? That is this as the y coordinate. Let me put y star. And for the z coordinate, it's 0 because it's on the z coordinate, z axis. So, and this star is what we want to figure out, right? That is the half width of the cured line at the surface. And also we know at this point, the energy exposure is EC. So we can easily substitute EC to here and substitute y star and 0 to this equation. And it turns out you will have this term removed because it's 0. And also you have EC known and you have this one. And the only unknown here is this y. And that is what you want to compute. So after some calculation, you will have a y to be this. And but that's only a half width, right? For the whole width of this cured line, you need to have it doubled. And that's the final solution for a width of the cured line at the surface, right? So the critical thing here is you have to understand when you look at this point at the surface, you are actually looking at a point with the exposure to be the critical exposure. And with this understood, you can easily figure out what will be the width, the half width, by utilizing all these knowns to and substitute them to this equation. All right, any question? Okay, that's good. So also, if there's a there is a question, basically we don't know this. I mean, usually it's supposed, usually this critical exposure is given, but let's say somehow we missed the information from the manufacturer of the resin. So we have no idea about the EC, but instead we have the width of the cured line at the surface. Then how you come up with EC? Any idea here? So any suggestions? Okay. So I mean, first thing first, do you understand what am I asking? Any question about my question? So my question is, if you know this width, but you don't know what is EC for some reason. I mean, usually EC is given. Then how you figure out EC?
Would you just use that first equation and plug in for y?
Exactly. Yeah, that's even simpler than this. So what you want to do is just substitute the width here. But one thing you want to be very careful is you need to know what is given. If it is given this length, and you need to divide it by 2, such that that will be the y coordinate at this point. So that's the only trick here. And other than that, there's nothing special. Basically, you just substitute the y coordinate at this point, and because z equal to 0, still this one is nothing. And it turns out you will have the EC, right? But I mean, that could be the case if you missed the information of your resin from the manufacturer. But same thing, utilize this equation. All right. Yeah. So any question about that example? Okay. Okay, good. I think we can move on the lecture. So in the photopolymerization, there's still curling and possible torsion happens. And as we mentioned a little bit, because of the shrinkage of the layers, that could cause some of the problems. So the problem is the shrinkage for different layers has different rate. Basically, there will be more shrinkage for the newly added layers compared to the original solidified layers, such that there will be a force pulled on these layers, and turns out that results in the curlings, like the one showing here. So there are multiple ways to avoid such curlings. For example, if you figure out what will be a better material which have less shrinkage due to this solidification process. Also, for the same model, you want to reorient the part such that the shrinkage does not happens in the critical regions, critical direction actually, right? So that would be a good strategy in case you cannot change the material. Also, another thing would be the support material. Because the support material, just imagine if you have support to pull this region downward, and that will prevent the shrink, this curling quite significantly. And that will be another possible solutions for this curling. But again, if you have the more support material, that could cause troubles, especially when you need to process, post-process those support. And that could also cause the surface accuracy and feature distortion when you remove the support material. So there's always a trade-off between the amount of support versus the difficulty of post-processing, right? You want to be careful when you decide to add support material. So other post-processing for the stereolithography will be this electroplating processes. So what you could do is you use this process to have a layer of metal on the surface of the built part from the stereolithography. And as you can see here, there are some nice nickel plated SL parts. And it functions for the handheld air compressors, which is shown in this figure, right? So there are several steps for the plating. I mean, similar to those who which are manufactured using other processes like injection molding. So first thing first is to make the surface electrical conducting, right? Basically, you want to make the surface to extract the electric charges, right? And the second one is to place a very thin layer of electroless nickel plating. And because of the surface of the parts have been electrical conduct, I mean, have been processed to be electrical conducting. So these nickel particles will be tightly extracted to the surfaces. Then we can electroplating with coppers. And the final step would be you put another electroless nickel plating or not. I mean, that's some optional steps. But with this conducted, you will have the plastic part to be electroplated for some applications, like the one shown in the previous slides. So another very interesting application, I would say is by far it's the most successful applications in the customization of using 3D printing. That is the Invisor Align braces. I don't know if any of you have used this, but the idea is instead of using those metal braces, they developed this polymer-based braces, which does the same job as the metal ones. And compared to the conventional metal ones, it's invisible. You don't need to wear it all the time. And because it's transparent, so it looks, I mean, it looks nicer when you wear it. But what it does is the software will create the steps of tooth movement. So there will be a couple of aligners, usually 12 to 48 aligners. And each of them is worn for about 6 weeks. That means you need to always change the aligners with this with your teeth movement progress. And basically, this transparent aligner, teeth aligner, is manufactured using this stereolithography machines. And it makes like around 100 unique aligners per build. And the material of this is the polycarbonate or polyurethane with 0.03 to 0.04 inches thickness. So for the polycarbonate material, it's pretty rigid. So just basically it is the same material as your credit card, right? Just to think of how rigid your credit card is. So in that sense, it is strong enough to reinforce your teeth to move to the proper position. And let's look at its process. Let me show you this.
The idea of mass customization is really basis of the company's existence. The idea that originally sparked the whole thing was, can we use digital technologies to kind of bring the science of teeth straightening into the next generation? When Invisalign started, 3D printing was primarily used for prototyping in a limited number of parts. So what we had to do is really figure out how to make that into a production process.
3D printing is really kind of the foundation of our manufacturing process. It's the starting point. When we make a mold for every stage of a patient's treatment, we use 3D printing to make those molds.
If you think about an injection molding type of process, where we're only producing the same type of part, millions of those, so that's been done before. Or you think about a very specialty 3D printing application where each part is unique, but they're produced in a small quantity. What we've done at Align is really combine those two. We've treated almost 6 million patients, and the growth is actually accelerating. We produce about 320,000 parts every day.
From a support perspective, 3D Systems has been instrumental in helping us get to where we are today.
What makes Align's mass customization so unique is not only are we producing millions of parts every month, but each one of these parts that we produce is unique. And this is really the, as far as I know, the only true example of mass production using 3D printing.
Okay. So one thing I want to clarify here is, I just realized I didn't make it clear. That is this one, this final product. This final product actually is not directly manufactured using the 3D printing. Instead, they 3D print the teeth model, actually the modified teeth, because you want to have your teeth move. Then the software will generate how it looks like if your teeth have little movement. And that model will be printed, 3D printed. So that model will be, then the 3D printed teeth model will be used for a die punching. Basically, if you ever learn the manufacturing processes or material processing, you know how the metal die punching, right? So you have your tool there, and you have your metal sheet, and after a punch applied, the same metal sheet will be formed in the shape of of the die, right? So it's similar to the metal forming. Basically, they utilize the 3D printed teeth as a die and utilize this polycarbonate sheet material and then there will be a forming process happens, and it turns out that will be your final liner produced. So they skip this process, this forming die punching process, but just want you to have a correct concept of how they actually do. So any question about this? Okay, good. So another critical part right now hasn't been solved in this invisible brace business is how to come up with the models for the teeth movement. So as you can see here, they have a large site and many people are sitting in front of computer. So these are the 3D modeling expert with some of the dentist knowledge equipped. And their job is to design these 12 to 14 aligners. So these are not generated automatically. Actually, it's still manually generated or semi-manually generated. It still rely on the people's expertise and experience. So that's why they have such a large team to come up with the model. And I think that will be a critical point in their business. Basically, if there are some software to automatically generate a model, that will be the game changer, right? That will increase the efficiency substantially, right? So also there's another applications, that is the custom hearing aids, right? So for the hearing aid bud, the requirement, I mean, it's preferable to have the customized ones. And again, the additive manufacturing or 3D printing would be the best fit to produce such kind of customized 3D print. But as you can see here, there are some companies, they 3D print the 3D the hearing aid, but it's shell actually using the stereolithography based method. Of course, there requires some manual assembly of these shells with the electronics components. So again, for this kind of process, the future direction would be how you come up with a method to integrate the assembly of the electronics component with the 3D printed shell automatically. And that will be another challenge problems. But overall, you can see how useful the stereolithography for those customization applications. So also for the carbon, you remember the CLIP process, the continuous liquid interfacing process. So the application they demonstrate right now is they work with Adidas to produce the axle of the running shoes. So basically, they come up with a lattice structure, which is those thin plate, thin frame structure, which are lighter and could absorb the impact better. And these 3D print such structure as the axle of a running shoe, and they showcase their products, but the price is pretty high. I think right now only those maybe the professional athletes could afford it. I mean, could justify the cost. And there's a long way to go, I would say, to make the customization available to everybody, to most of the individuals, right? There's a long way to go. So I think I can play this video for you, and that will be the end of this section, which is the stereolithography. Let me share the screen.
Well, at Oticon, we've recently moved into a brand new 162,000 square foot facility. And the beauty is that we were able to do that and design it based on our 100 years of product design and manufacturing experience. So we were able to lay the facility out, taking advantage of that to
What? It seems the internet is not stable.
optimize productivity and efficiency and really streamline the workflow. In addition to that, I think this expansion has allowed us growth for the future. So we were able to put the infrastructures in place to keep pace with the growing demand. It also enabled us to increase and upgrade all of our manufacturing equipment. And part of that manufacturing equipment consists of the SLA process. Now, for those that don't know what SLA is, it's called stereolithography apparatus. It's kind of a tongue twister. But what it means, it's really a great ability to take advantage of the new technology to create shells. We're able to double capacity and at the same time make a much more cosmetically attractive, smoother finish, comfortable fit product for the custom side of the business. Oticon produces a variety of BTE instruments and custom instruments to the marketplace. With the introduction of the Invisible in the Canal product Antigua, there is a growing custom product demand out there. With today's advances in technology, as well as the optimization in the design of making the product, we can make it smaller, comfortable fit, and the hearing care professional can fit a wide variety of hearing losses. And it goes beyond technology. Just because you have technology will not ensure you have a good performing product. It takes people, and people are a key foundation within Oticon. So it's a combination of the technology and how to use it, using the people, using their understanding of what's important to make a good product. Put those two together. That's called success. I think it's important for the hearing care professional to understand, with this new technology, they still have a key role to play in the quality of the impression that they provide. And I'm often asked is, what does it take in terms of an impression to make a good quality product? And it's really fairly simple. It's one of consistency. Is when an impression comes in, does it go beyond the second bend? Ideally, 2 millimeters beyond the second bend, full canal. Use that otoblock. I think that's important so that we can get a full, good size impression, including the concha, because the concha is also very important for a manufacturer because that's going to determine our locking points. Once we get that impression, the process we go through is we scan it. When I say scan, what we do is we make, through 2 cameras, we take what's called a digital point cloud. That's roughly 100,000 measurements in 2 to 3 minutes. So we create an exact replica of the impression that we get in. So after we do the scanning, we create a 3D image of that impression. Again, an exact replica. Now we print it. Now when we print it, we use the new technology. And again, that new technology makes it very consistent. We can have a very consistent product. So again, it's incumbent that we get a good quality impression. If we have that, it goes through the process of the shell making, it goes to our assembly floor, and then the technicians will take those components, put those components into the product for a product that's consistent, comfortable, as small a size as possible. So hopefully when you open that box, when you get that delivery, not only you're happy, but your patient will be happy as well. The question that comes up is what happens if we don't have a good impression? The hearing care professional might think with the advances in technology that the quality of the impression may not be important as it used to be. And it's actually the opposite. Because now, with the advances in technology, we are making an exact replica of that impression. And it's even more incumbent on them today, particularly with the smaller the products, the deeper in the canal that we go. So it's very important that we understand the anatomy. And we do that through the interpretation of the impression. It's a teamwork to make a good fit. And the hearing care professional has the advantage of having the client right in front of them. We as a manufacturer, on the other hand, rely on the impression. So any information that hearing care professional can relate to the manufacturer. For example, let's say it's a first-time user. That would help us in the tapering process of the canal to make it easy for insertion, perhaps a more comfortable fit. On the other hand, if you know you had a previous issue with the user, like slippage because of a straight canal, minimal locking points, let us know. And let us know if it'd be okay to, for instance, add a canal lock. So these are the little tips that you can help the manufacturer with. There's a reason why they call them custom products, and that's because no two ears are alike. What does it take? It takes attention to detail. It takes a dedicated staff reading the instructions, and it's also that teamwork element, communication with the hearing care professional as well as the manufacturer working together to ensure a good fit that's right the first time.
All right. So actually, if you look at the two applications, I mean the hearing customized hearing aids and also the Invisalign, there is a common point or requirement. So can you think of what it is?
Would it be the scanning ability, like how well you can scan?
Exactly. That is what I want to point it out. So to start the whole story, you have to have the scan, the 3D scan. And that is critical for both of the two applications, right? Without an accurate 3D scan of your teeth, it will be problematic for the software to for the the expert to design the 3D model of the corrected teeth model. And similarly, in the customized hearing aids applications, actually the man in the video, he mentioned a lot of how good the impression or how good the model of the scan would affect the final quality of the product. In that sense, you can see the critical point would be the data acquisition, 3D scanning. But actually, other than these two applications, for some other applications, like how about you want to have customized shoes or customized like clothing? Why these you rarely find applications for such application in such domains? The reason is it's really hard to have a good scan for such applications. It is different because in either the teeth, the teeth aligner application and the hearing aid application, you have really skillful professionals help you scan the data for you, right? The dentists are considered as the most skillful group of people, and also the hearing care professionals. They have the skills to properly operate the devices and also make the scan as possible, as accurate as possible. But that's really hard for people who work in a mall to scan your body, and you don't want to be scanned many times, right? And because of this lack of ability to 3D scan, to have an accurate 3D scan, that causes many applications cannot step out at the very beginning. In the very beginning, this is not possible. Then the whole pipeline will not work. So you can see how critical for the digitalization of the model to be conducted in such kind of a new pattern of business or technology. Well, that's pretty much all for the stereolithography. Let's have a little break, and let's come back at 11:05. All right. Let's continue. So let's talk about another process, which is the select laser centering. So what is selective laser centering? Let me play a video for you.
Selective laser sintering, or SLS, is a rapid prototyping technology that turns 3D CAD data into physical parts in a matter of hours. SLS is an additive manufacturing technology that uses powdered nylon 11, nylon 12, and PEEK materials. Parts produced are lightweight, highly durable, and both heat and chemical resistant, making SLS an excellent choice for producing production parts without the expense of tooling. The SLS process begins by splitting 3D CAD data into thin cross-sections or layers. The data is then transferred to the SLS additive manufacturing equipment. The machine then begins to create the first layer. After a leveling roller spreads a thin layer of powdered material across the powder bed, a CO2 laser traces the cross-section on the material. As the laser scans the surface, material is heated and fused together. Once a single layer is complete, the powder bed is lowered to make room for the next layer. More material is introduced from the powder cartridge and rolled out smooth, while unused material is recycled. The process is repeated, building layer upon layer until the part is complete. As SLS parts are built, they are encompassed by unsintered powder, which provides supplemental strength and eliminates the need for support structures. Complex designs and assemblies, once thought impossible, are now being redesigned with SLS as cost-effective integrated structures. Solid Concepts manufactures parts utilizing nylon with property-enhancing fillers to create rugged SLS parts suitable for a variety of prototype and production applications. Typical uses for SLS include tools and fixtures, fuel tanks, flight-rated components for unmanned aerial vehicles, automotive designs, air ducts, architectural models, and artistic sculptures.
Okay, so the process actually is basically that will a little similar to the stereolithography, which which is the SLS also utilize the laser as the power source. So it will solidify the powder, polymer powder or plastic powder. And a leveling roller will spread out the thin layer upon the existing layer. So the laser beam will scan over the powder bed, and the region to be scanned will be solidified. And once one layer is solidified, the whole platform will move downwards by one layer thickness. And then the leveling ruler will spread the material again, and the laser scan happens again to cure, to solidify the powder. So the good thing for SLS is it does not need a support material, because the build part is supported by the powder, the excess powder, right? So what happens for the material particles? So basically, there will be a centering or melting. So as you can see here, originally the material powder sorry, is separate. There's no connection between them. So when the melting or sintering happens, there will be some adhering happens to connect those particles together. And if there's a more energy input, there will be a larger area of connection. So this is how it look like when the particle is centered or melt. And there are different powder consolidation. One is the solid state centering. So there's no melting happens. So basically, it will have the latest bonding between the particles. And there could be some liquid phase centering. And there will be two components coexist. One is the solid particle, another one is the liquid state particle. And that's the liquid phase centering. Also, there are partial melting. So the full bulk of particles do not melt, just the skin. Ultimately, we will have a full melting. So that will be quite close to a full density. As you can see here, from the solid state centering towards the full melting, you can see this particle adhesion will become larger and larger, but as a result, it will require higher and higher energy. So there are different methods utilize different of these centering or melting. If you want to have more melting or more centering, you probably want to have a more powerful energy source. As you can see here in the select laser centering, what happens is similar to the stereolithography. That is a trace of the scanned region will be consolidated. And again, you have the hash spacing, which is similar to the pitch, right? In the SLA process. Also, it is laser based, and the laser power will be the primary process parameter as well. Also, if you are talking about nylon as a material, usually the power of the laser is 2 to 35 watts. Laser spot size, typically 400 microns. And scanning speed, 500 to 3,500 millimeter per second. And again, this hash spacing. As I mentioned, this hash space will determine this region, will determine the size of void regions. So definitely you want to have an appropriate hash spacing such that this void will be minimized. Also layer thickness, that is this this height, right? This height of the layer. Sorry. Another parameter is the powder bed temperature. So during the process, the powder bed is heated up. I mean, just think of the even for the fused deposition modeling, you want to heat up your build platform. That is because you want to have you want to minimize the temperature difference between the this scanned trace and the other material neighboring to these regions. And that will be helpful. I will introduce more details about why you want to heat it up, heat the powder bed temperature, heat the powder bed platform to be a higher temperature than the normal, the room temperature. So basically, for the stereolithography process, there will be a chamber. And this chamber will be heated up about 10 degrees Celsius below the melting point of the powder. So it is the whole chamber is really in a high temperature. And that will increase the laser scan speed. Because if you do not heat it up, heat up the entire chamber, then you probably need a very very powerful laser, or you really slow down the laser scan, right? Also, this temperature, if the temperature in the whole chamber is raised up to this level, the residual stress for the built part will be minimized, will be reduced, because again, the shrinkage of the plastic will be minimized by reducing the temperature difference between the environment as well as the built part, right? So that's the reason why we need to heat up the whole chamber. Another thing is we have a nitrogen atmosphere in the whole space. That is because if you have the air, the normal air inside, there will be oxygen there, and there will be the oxidation of the nylon powder happens if we directly use the air, the normal air in the chamber. So that's why the nitrogen atmosphere is filled in the whole chamber to reduce the oxidation of the powder. Any questions so far? Okay, so as I mentioned, it's still the thermoplastic utilized in the stereolithography, and primarily the nylon is the dominant of the material used in the SLS. Also, some carbon material could be utilized as well. And here show you some of the material could be used in the SLS process. But I would say pretty much nylon is the best choice among different materials. So if we talk about the thermoplastic, there will be some discussion on its phase and transition temperatures. So for the semi-crystalline thermoplastic, the gas transition temperature is around or below the room temperature, right? And there will be a distinct melting point and subsequent flowing of the material. Also, there will be a significant change in the volume above the melting point, melting temperature for the semi-crystalline thermoplastic. But for the amorphous thermoplastic, there's no clear melting point. And the glass transition temperature is around 100 degrees Celsius, which is really high compared to the semicrystalline thermoplastic. And so after the glass transition temperature for the amorphous thermoplastic, it will gradually soften up to a point that will, at that point, the material began to flow. And this point is of temperature is usually represented using TF, which is the flowing temperature. And the glass transition temperature and melting temperature, that really depend on the molecular weight of the polymer. So if you look at the molecular weight of the polymer, you probably can tell, at least have some sense about the glass transition temperature and the melting temperature. So as you can see here, the different thermoplastic are divided into different groups. Some of them are crystallines or semi-crystalline. Some of them are the amorphous thermoplastics, right? And basically you want to know these before you make decision to select materials for certain applications. So you might ask how you come up with these temperatures. And there are some standard experimental setup to determine the phase transitions. Basically, this DSC, that is differential scanning colorimetry, actually, it measures the amount of heat needed to raise temperature of the material a certain amount. So basically, it will estimate this difference between and after certain, the difference of the heat between and after you raise up the temperature. So for the semi-crystalline material, it exhibits melting peak during heating and a crystalline dip during the cooling. And the powder bed temperature should be maintained above this TC until build is complete. And the TC represents the temperature of crystallization. If you look at this, sorry, this graph, it tells you the difference. So one important thing you want to keep in mind is there are always two graphs for heating and cooling. As you can see here, this upper curve is the phase transition curve for heating, and this one is for cooling. So that is very interesting. You cannot just use one curve to predict the behavior of the material during this process. Because of during the process, there will be both heating and cooling happens for the thermoplastic powders. And you want to check both of the two curves to give you some ideas. And there will be a melting ranges for the thermoplastics. So the ideal polymer has a narrow melting range. That means when the melting begins, it will take very narrow range after it's fully melt. And that is the desired property for the polymer. And as you can see here, if we look at the two graph, one is PA12, Another one is PA6. And obviously this PA12 material has more narrow melting range compared to the PA6. That gives you the indication that PA12 is more superior than the PA6 in this SLS process, right? So these are the important points you want to look at if you have a material and you have such a DLC plot for the material, and that will again help you make decision when you make choice of the material. And the crystallization of the polymer material basically can be also checked through this the CSS curves. So the rate of polymer crystallization is at a minimum near the melting point, and it's at a maximum between the glass transition temperature and the melting point. So that is how you look at if you have such a chart. And the cold build channel will have a low crystallization rate, and that is the completion of the print. Another very important thing is you really want to avoid the polymer that the melting temperature and the crystallization temperature windows overlap. That is because there will be the significant crystallization to occur in the lower layer during the building. And that's undesired property for such a material. So that's what you want to look at it. So another property for the specifically thermoplastic is the melt viscosity. And basically the viscosity of the polymer at processing temperature should be low enough such that it will flow out to the full density before the temperature falls below the melting point. So again, this melt velocity is related to the molecular weight of the polymer. And the good thing is it's almost a linear relationship to the molecular weight. But the low melting velocity tend to produce high shrinkage. That is undesired, right? Because of the high shrinkage will cause the material, the built part to be deformed or curlings. So there's always a trade-off for the material properties. I mean, if you have a low melting viscosity, then you probably will suffer from the high shrinkage. And the only thing you can do is to find a balance, right? So another concept is this melt flow index. And it measures how well the molten plastic flows at a given temperature. It is international standard defined. And the ease with which melt SLS powder flows will changes every time when it is heat up. So if we look at this video, you can have some more intuitive understanding about it. Let me try to play this video. So here shows you how you measure the melt flow index. See, these are the particle of the plastic. and this will be melt. So you can, as you can see here, this molten plastic has flown through these tubes. So that's how this could be measured, how the molten plastic flows, how easy it flows to be measured. And basically, this melt flow index describes the polymer chain's length, and it increases with time at the elevated temperatures. And that is the indication of how easy the plastic, molten plastic, will flow at certain temperature. And what is the effect on the mechanical properties? So basically, the tensile strength will decrease. That is because the density of the material becomes lower. On the other hand, the elongation of the material increases. That is because the high molecular weight. If you look at this this graph, gives you the tensile test and the elongation of this PAGF polymers. And as you can see here, the horizontal axis measures actually this is the elongation percentage on the right hand side, and this is the yield strength on the left hand side. And basically, these curves measures how many times you use for the thermoplastic. And as you can see here, the more the more times you use the thermoplastic, its tensile strength will decrease dramatically. On the other hand, its elongation increases. So in that sense, we need to understand how we could reuse and recycle the powder. Because of even the powder have not been melt during the process, you can only reuse it for certain times, for certain amount actually. So what you usually do is for the powder, you use the 1/3 new powders and 1/3 powder from the overflow beans. So where is the overflow bean? Because there is the leveling roller move to spread the material, and there will be some excess powder to be pushed into the overflow beans. And so basically, you take 1/3 powder from this overflow beans, and another 1/3 from the used from the build chambers. So if you ever remember what happens when the part is built, basically you need to dig out the part from the whole box of the powder, and there will be quite a bit unused powder, because even it's unused, but it is heat up to a temperature. That is because the whole chamber is heated up to the temperature 10 degree below the melting point. So take 1/3 of the used powder from the build chamber and combine the 3 part of the powder as the one you use. That will be a good balance for both recycling the powder and also make sure the mechanical property of the thermoplastic powder does not degrade too much, right? That's a reason we want to use this rule of thumb to combine the powders. And sorry, there are some major players in the selective laser sintering area. 3D Systems, again, this 3D System is also a major primary manufacturer of laser sintering. And we have EOS, which is a German company, and ProWiz, also Formlabs, and Centerate. Actually, we have this Centerate machine in our lab. It's very small, we used to ask students to conduct experiment with the Centerate machine, but in recent few semester, we just stop it because it's really troublesome to use the selective lasering printer because of the post-processing, right? You need to take the part out from the printer, as well as you need to blow away the excess powder and do many cleaning process. In a small lab like the one we have, it's really troublesome. So instead, we don't use the Centerate machine. We don't let the student to use a Centerate machine anymore. Instead, we look at the videos and see how it works, and that's it. So there will be some design principles for the selective laser sintering, and that will be different from the one you use for designing parts for other process, because it has all the powder filled in the box, and sometimes you just, in most of the time, you don't need to care about the support material, and that changes the whole design quite a bit. And let's look at what it look like. And these rules, design rules, actually came up from the EOS document. And let's look at what they are. Sorry. So similar as other printing additive manufacturing process, there will be a stair-stepping effect because for the layer by layer manner of the printing. Sorry. But to minimize this stair-stepping, you want to make sure the angle of the plane between 0 to be 0 or larger than 20 degrees to the XY area. So if you look at this illustration, that is, you want only tilt your plane with respect to X and Y region only either be a parallel or larger than 20 degrees. That's the restriction. Otherwise, there will be a visible, quite significant stair-stepping effect for your part built over here. Sorry. And if the part you want to build using selective laser sintering, and there the part has pins and holes. So in order to make them to be printed successfully, basically the gaps of these pins and hole must satisfy this requirement. So that is in X or Y direction, the gap should be 0.3 millimeter to 0.5 millimeter. And in this direction, this gap should be 0.5 to 0.6 millimeter. That is because the building accuracy of the printer. So you have to have these features to be designed to which could be built under the given precision. Also, there are some variables to make the decision. For example, the gap between the bushing and the bolt, the length of the hinge, diameter of the bolt, wall thickness of the surrounding bushing, and the building directions. So these are all the variables you want to consider about if you have such a design which requires the consideration of the clearances. So for the assembly feet, basically, if you print the separate part, and then you need to assemble them together after prints, basically, you want to use 0.1 millimeter distance for the loose connections. That is, if you zoom in this, if you want to assemble this part with this base, and you want to have 0.1 millimeter distance if you want to have a loose connection, right? And that works for a male and a female part without a gap. That will, if that's the case, that means you are designing a press fit. You need to apply force when you want to assemble them together. If that's the case, then there's no need for a gap. Otherwise, you want to have a gap for more loose connections. Another point here is the fonts. So basically, when you build a part, you want to provide some information there. In the injection molding process, there are also ways to put text on it. And that is similar to what we have in the selective laser sinterings. And there will be a minimum font size 14 for every directions. And also there are some font types recommended by the EOS process, machines. So the limitation or the constraints of this process would also affect some of the features. For example, for the wall thickness, in the XY direction, the minimal wall thickness would be 0.45 to 0.7. And why there's a range? Because different machine could have different building precision, and there will be some variations depending on it. But in general, if you want to have the best result and a higher repeatability, it's better to have a minimal wall thickness to be 1.5 millimeter, which is 2 times than this upper bound of minimal wall thickness. So for the Z direction, the minimal wall thickness is equivalent to the one layer thickness. That is 0.1 or 0.15. Again, depending on the machine you used. So other than the wall, there could be some features like pins, right? And the minimal pin diameter is 0.8 millimeter. And again, this usually cannot be used. And you always want to have a more conservative setup when use these machines. And that is if you set up a minimal pin diameter to be 1.8 millimeter, that gives you the best result and a higher repeatability. So the principle here, as you may see here, you want to be conservative when you set up this. You don't want to be aggressive, and truly rely on the parameter the manufacturer of the machine gave you. Usually that will not work. You want to be more careful to set up these minimal size, feature size, right? Sorry. And here gives you the gaps. Basically, the minimum gap size also depends on the wall thickness of the part. It's similar as the wall thickness. As you can see here, if you have a 0.3 millimeter wall thickness, well, you pretty much have all these gaps printed successfully. But the minimum wall thickness becomes larger and larger, and then you will have some thinner holes, or thinner gaps to be filled by the material. That is what you want to be careful about when you have these very thin gaps. And on the other hand, the minimum wall thickness the machine could build is limited. Then you probably want to change your design according to this wall thickness, minimum wall thickness. And similarly, the hole diameters. So basically, again, look at the wall thicknesses. As you can see, if this machine allows a minimum wall thickness 0.3 millimeter, and pretty much you can successfully build holes up to 0.6 millimeter. But smaller than that, it's really difficult to have it built successfully. So for a larger minimum wall thickness, probably only or even for 0.6, it's hard to build successfully. And when you have your design, you probably want to consider about it. And I know there will be some holes and other gap features on your design if you come up with some new idea. And that is restricted, again, because the hardware, the machine capabilities. And yeah, that's exactly what it happens on the finger. So in order to have a more efficient building and higher build speed, there are some design principles you want to keep in mind. So one principle is the cost is depending on the Z height and the part volumes. Again, the build time of this SLS depends on how fast the laser scan on the build platform, and also how to spread the material and how much time it costs for spread material, and also lower the build platform. So that's why if you have more layers, or if you have larger part volumes, then that will cost more time and material. So when you design your part, then try to design it as low as possible in the Z direction. And the stackable part will increase the fill rate, right? So for example, if you have you have such a design versus this one, and if you want to build them using the selective laser centering, of course this one will be better because it's scalable, right? And that will reduce the Z height when you build it. Another thing is the part volumes, right? If you could integrate multiple parts to one design, or use some like thin frame structure, lattice structure, reduce the material consumption, that will definitely help to reduce the part volumes. Also, if you have the a better design which could make the excess part, excess powder to be flow through, that will be a good design for consuming less materials during the during the process, right? So as I mentioned, it is quite quite significant time and effort for the powder removal. And these uncentered powder need to be removed. And that's related to how you design it. For example, if you have such a spiral tubes, and the diameter of the tube is small, or the length of the tube is really long, that could cause problems for the excess uncentered powder to be removed. Just imagine if you build this part and there will be all the excess powder filled in this tube. And to remove them out will be quite difficult. Instead, if you have, let's see, some tube like this, right? Basically, there's no, it will be very easy to remove the excess powders instead of such a complex shape. So when you design the parts, you want to consider about this as well. That if the powder is easy to remove, that will save quite a bit time, and also it will cause less problems because the powder could be hazard for the people to remove it. See, if you look at the video, the guy in the video wears a mask, right, to process the part after printing, and it is very it is very troublesome if you have if you have a closed room without any ventilation devices, and that could cause health issues for the people who process the part. So that is the selective laser sintering process. For the stereolithography process, actually it's even more troublesome. If you have some design that will trap the liquid resin in it. Actually, I have a friend who works in a lab, have such a stereolithography printer, and he designed a I don't remember what exactly he designed, but that's a really big part. And there's a hollowed region in between. And he just make the design without second thought, and directly hit the printing button. And after quite a long time building time, time to build, he came back to the lab and took out the part, and he figured out there are quite a bit liquid resin trapped in the center of the part, because he didn't consider about how this excess liquid resin to be removed. I mean, he should design some holes or some open features for the liquid resin coming out, but he didn't realize it, and turns out he has such a problems with all the liquid resin trapped in the part, and of course the part cannot be used. So that reminds you, you have to consider about this for different processes. For this selective laser sintering, you need to consider about the powder removal. For the stereolithography, you need to consider about the liquid resin removal. But different process, but similar consideration you need to have. All right, I think this is pretty much all for today's lecture, and I will post this selective laser sintering to the the lecture notes to my courses. And it's a very brief intro, because I mean, after all, we don't have a chance to play with it, but you really want to look at the lectures, and that is used quite widely in the industry. You might have a chance to play with it when you get a job and work for such a process. So that's pretty much all the lectures. Any question before I let you go? Oh, I want to. I forgot to mention that. That is for your homework too. I will release the grade and also the solution by tomorrow. That's one thing. Another thing is tomorrow. Next class, we will have our first midterm exam, and I will post it on my courses and send you a reminder email about the time and what you will do. So it's basically same time as this lectures, and at 10 I will post. On next Monday 10:10 I will post the question of the exam, and you have the roughly 2 hours to complete it, and you want to submit it by 12:15 I think, and that's it, and that's an open book exam, and yeah, that's pretty much what you need to do. Basically the exam will cover all the content before the stereolithography. Just to remember what will be covered, and yeah, that's it. That's pretty much all the information. Yeah, any question?
I had a small question.
Yeah.
Is it possible for you to upload the PowerPoint versions of the lecture slides? Because I know currently, I'm not sure if it's just me not knowing what I'm doing, but when I'm accessing the PDF versions, I can't see some of the additional, like when you work out problems and things like that, it doesn't show up on the PDF version.
I think I've all I uploaded are in the PowerPoint format.
Okay, maybe I didn't download them right.
Yeah, I think you want to download it to check the full features. If you open it on the website, some of the features cannot be utilized. You want to download it and find where the file is and double click on it using your PowerPoint, Microsoft PowerPoint to open it. Then you will have the full feature. Yeah, that's pretty much you want to do. Yeah.
Okay, yep, that's my fault. Thank you.
No problem. And on Friday there's a office hour from 2 to 2:30. And if you have any questions about the lectures, homework, or the exams, you can come over to this same meeting room, Zoom meeting room, and I will be there on this Friday. All right. So any other questions? No? Okay, that's good. Pretty much that's all for today's lectures, and thanks for your attention. Okay, see you guys.